Identifying systems with infinitely many solutions. Now, if you look at the first point on the slide, you'll remember from our previous lessons that we've been focusing on using the substitution method to find a unique solution. Usually, when we solve a system, we are looking for a specific value for x and y, essentially finding that one single point where two lines cross each other. However, as we move into today's topic, we need to broaden our perspective. In mathematics, not every pair of linear equations results in that single, neat point of intersection. As you'll see in the following slides, there are special cases where the two equations we are given are actually just different algebraic representations of the exact same line. This means instead of two lines crossing at one point, they are actually sitting right on top of each other, which leads us to the concept of infinitely many solutions that we are about to explore. Welcome, everyone. Let's begin our new lesson on identifying systems with infinitely many solutions. Understanding the concept. When you apply the substitution method to a system of equations, your primary goal is usually to isolate one variable you're trying to get, for example, x by itself, so you can find its specific value. However, we encounter a special case when the two equations are dependent. This is just a mathematical way of saying they actually represent the exact same line. In this specific scenario, something unexpected happens. The variables will cancel each other out entirely during the substitution process. Instead of the algebra leading you to a specific value for x or y, you will find yourself left with a mathematical statement involving only constants. We will explore exactly what that looks like and how to interpret it in the next slide. Now that we've established that not every system of equations results in a single intersection point, let's dive deeper into what actually happens during the algebra. The result and interpretation. Now that we understand that the variables might disappear during substitution, let's look at what actually happens to the equation and, more importantly, what that tells us about our system. First, let's look at the result. When you perform the algebra, you won't find a specific value for x or y. Instead, the variables will vanish, and you will be left with a simple mathematical statement where both sides are identical. For example, you might end up with 5 equals 5, 0 equals 0, or negative 12 equals negative 12. So, how do we interpret this? Since a statement like 0 equals 0 is an identity, meaning it is always true regardless of what values you plug in for x or y, it tells us something very important. Any point that works for the first equation will automatically work for the second one. They aren't just related, they are essentially sharing the same set of solutions. Finally, let's visualize this geometrically. If you were to graph these two equations on a coordinate plane, you wouldn't see two distinct lines crossing at a single point like we saw in our previous lessons. Instead, the two lines are coincident. This is just a mathematical way of saying they lie exactly on top of each other, forming a single visible line. Because they overlap perfectly, every single point on that line is a solution to the system. Step-by-step procedure to identify infinitely many solutions. First, to determine if a system has infinitely many solutions using the substitution method, you should follow these 4 specific steps. Step 1. Isolate one variable. You'll start by picking just one of your two equations. It doesn't matter which one, as long as it looks a bit simpler. Your goal here is to rearrange it so that one variable, let's say x, is expressed entirely in terms of the other variable, y. Step 2. Substitute into the second equation. Once you have that expression for x from the first step, you're going to take that entire piece and plug it into the second equation where the x used to be. Step 3. Simplify the equation. Now, you'll use your algebra skills to combine like terms and clean up the expression. This is where the magic happens. Finally, step 4. Analyze the final statement. This is the most critical part. You need to look closely at what remains after you've simplified everything. If the variables completely disappear, meaning they've canceled each other out, and you are left with a statement that is undeniably true, such as 10 equals 10, then you have found your answer. The system has infinitely many solutions. Now that we understand the theory behind what happens when lines overlap, let's look at the practical side. I want to give you a clear, step-by-step procedure so you know exactly what to do when you encounter a system of equations and you're unsure of the outcome. We are going to see this exact process in action in the next slide with a real-world example involving shopkeepers, so pay close attention to how these steps unfold. Real-world example. Now that we have understood the theory behind coincident lines, let's put it into practice with a real-world example. Imagine we have a scenario involving two different shopkeepers, both describing the price of a gift hamper that contains notebooks, which we will represent with the variable x, and pens, represented by the variable y. The first shopkeeper tells us that the cost of 2 notebooks and 3 pens is $13. The second shopkeeper says that the cost of 4 notebooks and 6 pens is $26. At first glance, these might look like two different pieces of information, but let's see what happens when we solve them algebraically. In step 1, we translate these sentences into mathematical equations. For the first shopkeeper, our first equation is 2x plus 3y equals 13. For the second shopkeeper, our second equation is 4x plus 6y equals 26. Now, following the procedure we discussed in the previous slide, let's move to step 2, where we isolate one variable. Let's take our first equation and express x in terms of y. If we subtract 3y from both sides, we get 2x equals 13 minus 3y. To get x by itself, we divide the entire side by 2, giving us x equals 13 minus 3y, all over 2. In step 3, we perform the substitution. We take this new expression for x and plug it into our second equation. So, we replace the x in 4x plus 6y equals 26 with our fraction. This gives us 4 multiplied by the quantity 13 minus 3y, all over 2, plus 6y equals 26. Now, let's move to step 4 and simplify this expression to see what the algebra reveals. First, we can simplify the fraction by dividing the 4 outside the parentheses by the 2 in the denominator. This leaves us with 2 multiplied by the quantity 13 minus 3y plus 6y equals 26. Next, we distribute the 2 into the parentheses, which gives us 26 minus 6y plus 6y equals 26. When we combine our y terms, the negative 6y and positive 6y cancel each other out completely, leaving us with a very simple statement. 26 equals 26. Finally, in step 5, we reach our conclusion. As you can see, the variables x and y have completely vanished, leaving us with the statement 26 equals 26. Because this is a true statement, we have confirmed that these two equations are dependent. This means that, just like we learned, there are infinitely many combinations of prices for notebooks and pens that satisfy both shopkeepers' descriptions. As we will see in the next slide, this is the hallmark of a system with infinitely many solutions. Key takeaways. Now that we have worked through that practical example, let's take a moment to summarize the key takeaways from today's lesson so you can solidify what you've learned. First, let's talk about variable elimination. As you saw in our step-by-step calculation, when you are dealing with a system that has infinitely many solutions, the variables don't just move around, they actually vanish entirely during the substitution process. They simply cancel each other out. Second, keep an eye out for a true statement. When you finish your simplification and you are left with a mathematical identity, something like a equals a, this is your signal. This result confirms that the two equations are coincident, meaning they are essentially the same. Third, we use a specific term for this, a dependent system. We call it dependent because the two equations are not independent of one another. Rather, one equation is simply a multiple of the other. If you look back at our shopkeeper example, you'll notice that the second equation was just the first equation multiplied by 2. Finally, let's visualize the graphical view. If you were to plot these two equations on a coordinate plane, you wouldn't see two distinct lines crossing at a single point. Instead, the two lines overlap perfectly, sitting right on top of each other. Because they are the same line, every single point located on that line serves as a solution to the system. Before we wrap up, I want to highlight a few common pitfalls to avoid, as these are areas where many students lose marks in exams. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even if you understand the concept of coincident lines, it is very easy to make a few specific errors during your calculations. Let's look at 3 common mistakes to avoid. First, be very careful not to confuse a true statement with a false statement. As we saw in our example with the shopkeepers, when you end up with something like 5 equals 5, that is a true statement, which tells us there are infinitely many solutions. However, if your variables cancel out and you are left with something like 5 equals 0, that is a false statement. In that specific case, the lines are actually parallel and never touch, meaning there is no solution at all. This is what we call an inconsistent system. Always double-check if your final numerical statement actually makes sense. Second, a very common mistake occurs when students see a result like 0 equals 0 and mistakenly conclude that the answer to the system is x equals 0 and y equals 0. Please remember, that is not the case. 0 equals 0 is simply a mathematical identity. It is a general truth. It doesn't mean the coordinates are 0. It means that every single point on the line satisfies the equation. Don't let the zeros trick you into thinking the solution is just the origin. Finally, try not to stop too early. It might be tempting to look at the coefficients in the equations and immediately guess that there are infinitely many solutions. While you might be right sometimes, you shouldn't rely on guesswork. Always complete the full algebraic substitution process to prove that the variables truly vanish and leave you with a true statement. This ensures your work is mathematically sound and prevents you from misidentifying a system. With these precautions in mind, you should be well equipped to identify these types of systems with confidence.